Okay, second part of the 2D laws, Gay-Lussac's law. All right, Gay-Lussac's law is the relationship between pressure and temperature. And very similarly to Charles' law, Gay-Lussac's law shows that as the pressure goes up, the temperature goes up. And as the temperature goes down, the pressure goes down. Namely, this relationship is linear. And following the same logic as we did before for the previous problems, we find out that P is y, t is the x of this linear equation, and c is the slope. Once again, we assume that the intercept is 0. Solving for the slope means that we end up with p over t. Using two separate data points, we find out that p1 over t1 and p2 over t2 have to equal the same slope, so p1 over t1 must equal p2 over t2. This is Gay-Lussac's law, and this works out as long as the volume is constant and you don't change the amount of gas. Alright, now a problem of this sort shows that you basically have to have two sets of pressure and two sets of temperature. So let's check that out. We're being told that there's a gas of 740 millimeters mercury worth of pressure at a temperature of 70 degrees Celsius. So we have pressure and temperature mentioned once. Now, we're also being told that the pressure is lowered to 540 millimeters mercury. Notice that it's saying 2, so we're not lowering it by 540, but to 540. So this is the final pressure. But pressure is being mentioned twice. And then we're being asked what is the temperature at this final pressure if the volume is constant. So the temperature is mentioned once more, so we have two sets of temperature, two sets of pressure, and then the volume we're literally being told is constant, so we don't worry about the volume. But because there's two sets of pressure and two sets of temperature, this tells you this is Gay-Lussac's law. P over T equals P over T. Alright, now here we're looking for the second temperature, T2. So what you would need to do, if you like, is cross multiply both sides by T2 and then cross multiply both sides by T1 over P1. Okay, and what that will do is basically rearrange the equation this way. So T2 goes to the left side, then you end up dividing both sides by P1. P1 is in the denominator. You end up multiplying both sides by T1, so T1 ends up in the numerator. Okay, now, like before, we're dealing with temperature, so the temperature has to be in Kelvin. Even though here you don't need to cancel out temperature units, you need to have this in Kelvin. If you keep it in degrees Celsius, your numerical answer will be wrong. So the 70 degrees Celsius needs to be changed to Kelvin by adding 273 to it. Alright, now P2 is on the numerator, so we need to find out P2, and P2 is 540. T1 is associated with P1. P1 is 740. So T1 has to be the 70 degrees Celsius, right? So we have 540 on top, P2, 70 plus 273 to turn it into Kelvin for the temperature, and at the bottom we have P1, which is 740. Since the units of pressure are the same, there's no conversions that need to happen. They will cancel out. The temperature in Kelvin is now 343. And upon carrying out the calculation, we find out that the temperature is 250 Kelvin. And notice the following. The temperature has gone down. We started at 70 degrees Celsius, we're now, or conversely, we started at 343 Kelvin and we're down to 250 Kelvin. And the pressure has also gone down. It went from 740 down to 540. So this is a way for you to check whether your problem makes sense or not. Alright, Avogadro's law. Avogadro's law is very similar. It follows the same logic, except that now we look at the interaction of volume with moles. And if you plot volume versus moles, you find out that there's a linear relationship. And for this linear relationship, we have volume on the y and we have moles on the x. And there's a slope associated with this line. The intercept, once again, is thought to be 0. So if you solve for the slope, you have volume divided by n. And if you take two data sets worth of points, you have v1 over n1 and v2 over n2 equaling the slope of the line, which means that v1 over n1 equals v2 over n2. This is known as Avogadro's law. And this works so long as the pressure and temperature remain constant. Okay. Now, this is actually the experiment that Avogadro did himself. And although we think of Avogadro in the context of Avogadro's number, it's actually this experiment or this law that is completely associated with him actually doing the experiment. Avogadro's number actually had nothing to do with him. He never found a number, he never calculated it, he never did experiments for it. But this premise of Avogadro's law was what led out to ultimately finding Avogadro's number. So that's why they kind of honor him in that way. All right, but now let's take a look at a problem that depicts Avogadro's law. We're being told that 6 liters of a gas sample at 25 degrees Celsius and 2 atmospheres contains half a mole of H2. Now notice here that volume, temperature, pressure, and moles are all being mentioned. Okay, so at first you might not exactly know where you're going with this, but if you continue reading, this says that an additional 0.25 moles of hydrogen gas have been added. All right, so now you have 2 sets of moles. The temperature is the same and the pressure is the same, so the temperature and pressure are not changing, so you don't even need to consider them anymore. But you're being asked for what is the new volume of the gas when you add this additional amount of gas. So you have 2 sets of volume and you have 2 sets of moles. This is telling you that you're dealing with Avogadro's law. V1 over N1 equals V2 over N2. And since we're looking for the final volume, we need to cross multiply by N2 to solve for V2. All right, now V1 times N2 divided by N1 is going to give us the final volume. So we plug in the values. V1 is 6 liters. N1 is the half mole of H2, but N2 is not 0.25 moles. It's 0.5 plus a 0.25 because you're adding the 0.25 moles to the original amount. So be sure to read the problem completely before you start checking in numbers, because the semantics completely could change the game of the problem entirely. So just be careful with that. Okay, so 0.5 plus 0.25 is 0.75 moles. And now the moles will cancel out, multiply the two numbers, divide by the denominator. You end up finding out that this is 9 liters worth of volume. And since you increase the amount of moles of gas, the volume went from 6 to 9 liters. It also increased. So this is a way of checking your problem, whether it's making sense or not. If the volume goes up, the number of moles has to go up. If the number of moles goes down, then the volume has to go down. Okay, so that's the premise based on Avogadro's law. Now in the next video, I'm going to show you and talk about the combined gas law, which is one of the 3D laws.